Hello, everyone. Welcome to the second quantum error correction session of the day. So we have two very exciting talks lined up. And first up is Ray Lee, who will tell us about locality versus quantum codes. So please, Ray.
All right. Thanks for the introduction. This is joint work with Sam Dai. The summary of our work is that we prove optimal locality versus parameter trade-offs for quantum codes in 2 dimensions. So I'll start by giving some background about the question we're studying. Then I'll tell you about our results. And with whatever time I have left, I'll say a few words about the proof. So quantum codes are the most promising avenue towards large-scale fault tolerance. We typically measure the quantum code by these parameters, n, k, and d. So quantum codes, they simulate logical qubits using imperfect physical qubits. And we usually let k denote the number of logical qubits and n denote the number of physical qubits. We also use this parameter d to denote the distance of the code. And this roughly corresponds to the number of errors that we can tolerate. Actually, it's more like the number of errors is more like d over 2. But in this talk, everything is asymptotic, so we're going to be fast and loose with the constants. And I'm going to make a lot of plots like the one on the right. So we've got k and d on the axes. And we measure k and d relative to n. So larger k is better because that's less overhead. Larger d is better. That's more error tolerance. So better codes are up and to the left. And we're doing this on a log scale, so halfway is root n as opposed to n over 2. So in this work, we study stabilizer codes. Our bounds also hold more generally for commuting projector codes. So stabilizer codes are the quantum analog of linear codes. So they're given by these n minus k stabilizer checks, same n and k. And these checks are n-qubit Pauli operators. So they operate on some subset of they operate on the n qubits. And here is an example of a stabilizer check acting non-trivially on 4 of the 25 qubits. And throughout, I'll use this term, low-density parity check, which you're probably familiar. This means that all checks of the code, all of the stabilizer checks, act on a constant number of qubits, constant independent of n. Okay. So these are the figures of merit we use to evaluate a quantum code. We study quantum codes under locality constraints. So the motivation is that physical architectures favor local interactions in low-dimensional embeddings. And this talk, low-dimensional means 2-dimensional. So the idea is that you lay out your qubits. You want to put your qubits often on a chip, and that means you're effectively embedding them in 2 dimensions. And in this embedding, we prefer local interaction. These are easier to implement. So what are local interactions? An interaction is 2 qubits in the same stabilizer check, because to correct a stabilizer code, we measure the stabilizers. So this 4-qubit check has 6 interactions. And an interaction is local if it's between a pair of nearby qubits. So in the embedding, the interacting qubits are close together. And formally, what do we mean by nearby? Well, we think of our qubits as being embedded in a root n by root n lattice. And an interaction is local if the qubits are a constant distance apart, so constant independent of n. And we call this the length of the interaction. So it is well known that if a code is local, meaning all of its interactions are local, then this severely constrains the quality of the quantum code. So there's these well-known bounds, the Bravey-ter Hall bound and the Bravey-Pullen-ter Hall bound, which says that any 2D local code satisfies d is at most square root of n and kd squared is at most n. So the less than with a squiggly means we're suppressing constants. So you might notice that the second bound implies the first bound. And so for 2 dimensions, we just really need to think about the second bound. But I state both of them here. One, because the first bound was they came up with it first, and also because our results will generalize both of these bounds in some sense. Okay. So in our plots, we have that this is kd squared equals n, and the local codes must be in trade-offs in the blue region, so below the line. Okay, and you probably know that surface codes saturate the BPT bound. So surface codes, they're usually stated as d equals root n and k is a constant. But by some simple modifications, like you can copy the code multiple times, you can actually get everything on the BPT bound. Okay. So we understand, what are the optimal quantum codes when we're constrained to be entirely local. So we study the question of what if we want better codes? What if we want codes above the BPT bound? So there's been a long line of work, and this is not all the codes now, but and they've culminated semi-recently in this breakthrough of asymptotically good LDPC codes. These are codes with linear rate and distance. So there's all these codes, and you could ask, for these codes, so obviously they're above the BPT bound, so implementing them you have to have some non-locality. How much non-locality do you need to implement these codes, or your favorite code that's above the BPT bound? Okay. And so the first thing to do is to formalize and make precise this question. And this was done by Baspin and Krishna, who studied this. So they asked, first, how many non-local interactions do we need? So how many pairs of interacting qubits need to be far apart? And secondly, how long must the interactions be? So how far apart must the long interactions be? So this is the question that was studied by Baspin and Krishna. They proved some bounds, which are shown on the next slide, and then we improve their bounds to be tight. All right, so now I'll give a summary of Baspin and Krishna's results. So they prove some bounds in this setting. So they prove 3 different bounds, and I'll show each of them. So first bound is they show that for D is more than square root of n, a LDPC code needs at least D interactions of length D over root n, roughly. All right, so this big omega, if you haven't seen it before, this is like the opposite of big O, so it means you're at least D asymptotically, so at least some absolute constant times D. And this big O with a tilde is like, or big omega with a tilde is big omega, but you're also suppressing log factors in addition to constant factors. Okay. All right, so one way to, so just to apply this result in one context, let's, so just to compare, you can think of the Bravither-Hall bound, think of this as a generalization of the Bravither-Hall bound. The BT bound says that if you're above the BT bound, you need at least one long interaction. You can't be entirely local. And this result is saying you don't just need one non-local interaction, but you need many long interactions, where many is given by omega d, and long is given by omega d over root n. So just to apply this to one example, so if you apply this to asymptotically good codes, so this is K and D are linear in n, this implies that a good LDPC code needs at least n interactions of length root n. And if you think about it, this is basically saying that they have the worst possible non-locality. So you can show trivially that any 2-dimensional LDPC code has n interactions of length root n. It has n interactions because every check contributes a constant number of interactions, so there's n interactions, period. And also all the interactions have length root n because you're on a root n by root n lattice. So this result is saying that good codes have like the worst possible non-locality up to these polylog factors. They also prove some other results. So for K is linear in n, they show that an LDPC code has roughly n interactions of length square root of d. And also they show that in the general parameter regime where K and D can be anything, the code needs this many interactions of this length. So d root K over n interactions of length square root of Kn over d. I'll also mention one other result in this direction. This is by Hong, Marinelli, Kaufman, Marinelli, and Lucas. And they show that when D is greater than square root of n, an LDPC code needs at least D non-local interactions of length super constant. Okay. And this little omega is like the strict version of big omega. So it's asymptotically bigger than square root of n. OK, so these were the prior results known for these questions of how many interactions do you need above the BPT bound and how long must the interactions be. Okay? So these are some very nice results. Already we can see some interesting consequences. So the question we were after is, one, can we do better? Like, are these bounds better, optimal? Can we prove better bounds? And also, can we unify these results? Like, there's kind of 4 different bounds, and they kind of all work in some are better in different parameter regimes. Can we find kind of one result that sort of says everything we need to say about this problem? Okay, so this leads us to our results. So our main result is the following. So in 2 dimensions, every NKD code above the BPT bound has at least m interactions of length at least L, omega m interactions of length omega L, where m and L are given by this. So m is max KD, and L is the larger of d over root n and 4th root of KD squared over n. All right, so again, you can think of this as generalizations of the BPT and BT bounds. So for example, the BPT bound says above the BPT bound, you need 1 non-local interaction. And we're saying that you not only need 1 non-local interaction, you need many long interactions. And so, so next I'll unpack what was going on in this L term, because it's a little bit scary, it's kind of complicated. So if you rearrange the definition of L, you will get that we need that L satisfies these 2 equations. So D is at most L times root n, and KD squared is at most L to the 4th times n. So in this way, you can see another way that our result generalizes the BPT bound and BT bounds. The BT bound, remember, it says D is at most root n. So this is saying that if D is greater than root n, if we're above the BT bound, then the further and further away we are from the BT bound, the longer and longer the interaction lengths must be. Okay. And similarly, the further above the BPT bound we are, the further above, the larger KD squared is compared to n, the longer our interaction lengths must be. And so it's giving this kind of smooth trade-off that as your codes get better and better, then your locality gets worse and worse. And so now what you can do is you can plug this into your favorite codes, and for your favorite codes, either the ones here or the codes that you come up with, you can get bounds on how non-local these codes must be. So for example, like for Baspin and Krishna, we recover this bound that good codes need n interactions of length square root of n. Okay, so now I'll make a few more comments about our results. Okay. So first, our results improve or generalize all prior results in all parameter regimes. Okay. So I've drawn these plots to plot m and L to help you visualize what's going on. So in these, I have D and K on the axes, and I've drawn contours for various values of m over here and L over here. Okay. So where do the prior bounds fit in? So our bounds improve Baspin and Krishna's results in all settings. In some cases, in the purple regime, we're just shaving polylog factors, so it's basically the same results. And in the white region, we are improving both bounds by substantial amounts, so by polynomial factors. So I guess we're improving m by this polynomial factor and L by this polynomial factor, and also shaving some polylog factors. Okay. So we improve it in all parameter regimes. In some cases, we're just shaving polylogs. In some cases, we're making more substantial improvements. And also, where does the other result fit in? So this result of Hong, Kaufman, Marinelli, and Lucas, this improves Baspin and Krishna's result by shaving polylogs in this particular regime of D is square root of n and K is a constant. Okay. So we improve these results, sometimes shaving polylogs, sometimes making more substantial improvements. Okay. Also, we generalize these results from LDPC codes to all stabilizer codes. So our lower bounds hold for all stabilizer codes, while these previous results both hold for only LDPC codes. So it's a more general lower bound. Okay. Lastly, I'll point out that like in Baspin and Krishna's work, our bounds work for general embeddings. So I mentioned before, I defined a 2-dimensional embedding as you put your qubits on a root n by root n lattice, and local means that are a constant distance. But you can also consider more general embeddings where the qubits just have to have pairwise distance at least 1, but you can put them wherever you want. Okay. And these are bounds. This also works when you allow a more general embedding. And lastly, I will mention that our bounds are optimal for all n, k, and d above the BPT bound. Okay. And so what do I mean by optimality? So our result covers all statements of the form, every code needs m interactions of length L. So that's the form of our statement, and what this is saying is that any statement like this that you could possibly prove is covered by our results. Okay. So I'll argue, or I'll show that both M and L are optimal in strong ways. Okay, and just to distinguish this from this, I call this M star in our theorem. Okay, so what could you try to do? You could try to potentially improve our result by saying that you need more than M star interactions. And maybe you don't even need to show that there's M star long interactions. You just want to show that there's more than M star non-local interactions, strictly more than M star. But this is actually not true. So it follows from the existence of good codes that there are codes with at most M star non-local interactions. You just take a good code of length roughly M star. This has M star interactions, and so that gives you this. In fact, it's not just at most M star non-local interactions. It just has at most M star interactions, period. Okay. So our interaction count, M star, is the best possible for our lower bound. Similarly, you could ask, well, could you improve the interaction length? Could you show that there's at least one interaction that's longer than L star? Right? We showed that there's interactions of length at least L star. Can you show strictly more than L star asymptotically? This also turns out to be false. Okay? So what we show in this work is we give a construction of codes that have no interactions of length strictly larger than L star. All the interactions are length big O of L star. Okay? And the idea behind this construction is we concatenate a surface code with a good LDPC code. And maybe the one way to think about this is surface codes are like entirely local. They're at one end of the trade-off where they're entirely local but have not so great parameters. And then you have the good codes which have optimal parameters and the worst possible locality. And when you concatenate them, you kind of get something in between. So you concatenate them with the right proportions. One thing I will mention about, and part of why I have this asterisk here, is that these codes are not LDPC. So one open question that's left by our work is like, what's the right bound for LDPC codes? Potentially, so for stabilizer codes in general, we get the right bound on L. But if you restrict yourself to LDPC codes, you could potentially prove a stronger no-go result, a stronger lower bound. So could you do that, or could you find an LDPC code that has our matching value of L? I'll also mention one application of our work to the stacked architecture. Okay. So the stacked architecture is this proposed architecture for implementing quantum codes. A code can be implemented in the stacked architecture if it has mostly local interactions. So most of the stabilizer checks are local. But it's allowed to have some non-local interactions. And the more non-local the interactions, the fewer of them you have. And so the original, so when Baspin and Krishna first introduced this architecture, stated this architecture, they had this quantitative trade-off of you need to have this many interactions of length at least L, but you can also consider more general distributions. And the idea behind the stacked architecture is potentially if you allow some non-locality, you could get codes beyond the BPT bound. And then also, you could limit the cost of these non-local interactions by measuring the local checks less frequently. So maybe you measure measuring the non-local checks less frequently. So maybe you measure the local checks every round, and maybe you measure the non-local checks less frequently. So one question that was left open by these works is whether hypergraph product codes could be implemented in the stacked architecture. And if you just plug in our results, it says that hypergraph product codes, you need many interactions in the intermediate length regime, which means that hypergraph product codes cannot be implemented in this architecture. And for this particular definition of the stacked architecture, Baspin and Krishna gave some bounds, and we improved their bounds. So our bounds are the red region, theirs are the dotted lines. And then there's this question of like, what are the optimal bounds for the stacked architecture? And in particular, I'm not aware of any bounds that, any codes that are above the BPT bound that exploit the permitted non-locality of the stacked architecture. Okay, I don't think I have that much time, so I'll just say a few words about the proof and mostly just show some pictures. Okay. So first, just at a very high level, what is the difference between our techniques and the techniques in Baspin and Krishna that allow us to get the tight bounds? So Baspin and Krishna, they use this very nice idea called the connectivity graph. And you can probably guess what this graph is. So this is a graph associated with a quantum code where the vertices are the qubits and the edges are the interactions. Okay. So what they do is they take this problem about bounding non-locality in quantum codes, translate it to something about the connectivity graph, use some graph theory results, and then translate it back into some result about how much non-locality you need. Okay. In this work, we don't translate it to the graph. We work directly with the geometry of the problem. And intuitively, this is just intuition, using the connectivity graph seems more difficult than using the geometry directly. And this intuition seems to be true in a different line of work that tries to generalize the BPT bound in a different way. All right, so I'll say a few words about just like what's the outer layer of the onion of our proof. Okay. So we reason about correctable sets. A set of qubits is correctable if we can correct the erasure of that set of qubits. And the main lemma we use is that something called what we'll call the ABC lemma. So this is saying that if you can partition your set of qubits into 3 sets, A, B, and C, such that A and B are correctable, then C bounds the size, the number of logical qubits. And intuitively, you can think of this as like if you can correct A and B, then somehow you need to have the logical information in C. All right, so now what's the game that we play? You assume for contradiction that our code has few long interactions, so it doesn't have the amount of non-locality we want. Then we derive a contradiction by finding A, B, and C, where A and B are correctable and C is small. Okay. So you assume it has few non-local interactions, and then you find A, B, and C. And then how do you find these correctable sets? You use these properties of correctable sets. These are these 4 properties. And I don't really have time to go into them, but just as one example, you can show it's true that any set of size less than D is correctable. This just follows from the distance of the code. And then you have these other properties, the union and expansion lemma, which you can use to grow your correctable sets. OK, so now I'm just going to flash some pictures, and I'm happy to say more offline or in the Q&A. All right, so our starting point is the proof of the BPT bound. And if you've seen the proof of the BPT bound, you might recognize this picture. So you partition your set of qubits into, you assume it has no non-local interactions. Then you partition your qubits into these sets A, B, and C, which are given by this picture. And then you can show that A and B are correctable, and C has size at most n over d squared. Okay, I'm not going to justify that because of time, but this implies that K is at most n over d squared. You rearrange, you get your BPT bound. Okay. So at a very high level, this is how the BPT bound proof goes. And this is the proof in their paper. So we start from the proof of the BPT bound. We don't start from this proof. We start from a slightly different proof. You can check that this partition of A, B, and C also works. So this will show that there's at least one non-local interaction. But we need to show there are many long interactions. To show there are many long interactions, you basically just do the same thing. And to show that there are many interactions, well, you have to do more work to make sure, because the long interactions might mess up all these arguments. But the idea is that somehow you're folding the qubits that participate in long interactions into A, B, or C. So I think when you're trying to show there's at least K interactions, you absorb them into C. And when you're trying to show there's at least D interactions, you absorb them mostly into B. OK, but that probably is just very vague, so mostly just showing the pictures. All right, so that's all I have. So the summary of our talk is we give optimal locality versus code parameter trade-offs for codes above the BPT bound in 2 dimensions. They can be applied to the stacked architecture, and our improvement over the Baspin and Krishna's work is that we use the geometry directly. Thanks.
All right, I think we have time for a few brief questions.
I have one comment and one question. So first of all, if you have sort of 1 or 2 or few long-distance interactions and then the rest of them are local, then I think automatically it follows that the stabilizer has LDPC property just because there is no space to put more.
OK.
Okay. And then secondly, once you start talking about long-distance interactions, there could be permutations of qubits that would give you a different set of long-distance interactions. Mm-hmm. And question is there sort of in your sort of statements, is there a way to say, well, if there is any other, then it will be sort of better or worse or whatever.
So your question is like, so our definition of long interaction depends on the embedding, and the question is like,
Correct.
what about other
is there
embeddings?
some universality with respect to a different embedding?
So I think our results say that if you have an NKD code, then no matter what your embedding is, you need to have many long interactions. I don't know if that answers the question.
Yeah. Thank you.
Hi, thanks for a nice talk. This is just for clarification. So how do you define dimension when you allow long-range interaction? For example, if you have 3D toric code, can you define it as a 2D code with long-range interaction?
How do we define distance when we define depending on the dimension? So everything I said is for two-dimensional embeddings. We have some follow-up work with Eugene Tang where we generalize it to larger dimensions, but that's not.
So you mean if you are considering 3D code, you have to embed it into 2D before you consider this?
No, so the follow-up work says that if you have a three-dimensional embedding, you need a certain number of long-range interactions, but it's not. I didn't present it here.
Okay, thank you.
You mentioned that the codes with the optimal parameters you found were not LDPC, but these concatenated codes with surface code on the inside. I'm guessing it's not a constant size surface code, but in some way dependent on the parameters of the LDPC. So what is the size of the surface code, and what was the reasoning for this working out? Why does this work?
So there's this, the concatenation between the surface code and the LDPC code. So I forget exactly what's the parameter, but it's if you're close to the BPT bound, the surface code is the whole code. And as you get closer to the parameters NKD get bigger, then the LDPC code is bigger. And in between, it's kind of proportional to how far away from the BPT bound you are. And sorry, what was the other part of your question? Why does this combination work? So the idea is that all the interactions are going to be basically within the interactions are going to be the interactions of the LDPC code, which are, I think, they're length L, I think, or L squared. And so they're within the LDPC code, and then because you're concatenating, there's also interactions between adjacent LDPC blocks. Yeah.
So for architecture design, one other concern could be the planarity of the code. I think one advantage with Krishna and Basmin's work was the graph theory results applied on the connectivity graph, giving also planarity-related bounds. In this framework, could you comment on planarity? Is that a straightforward way?
Right. So does our bound work for graphs with codes with planar embeddings? That's a good question. So immediately from this, you don't get it. Okay, I don't know off the top of my head. Maybe, but maybe not.